So today, our goal is to be able to do area problems using polar coordinates. So I'm going to do a really quick review of Calc 1 because this is what we're going to piggyback on. So in Calc 1, you had the problem of this nature, and you wanted to find the area under the curve. So what you did was you subdivided the region into n rectangles of varying sizes, and you could pick any point within the rectangle to square it off and so on. And then what you did was you found the area of the ith rectangle. Let's say that right there is xi minus 1, and that's xi. That would be x0, that would be xn. And you wanted to find this guy right here. So the area of the ith rectangle, as you remember, was f of wi, where that wi was just a random value in the ith rectangle. Make sure you're muted, please. In the ith rectangle. And then delta xi is just the difference between xi and xi minus 1. Then we could say a reasonable estimation of the area would be the sum from I equal 1 to n of this, where x ranges between a and b. And then we could say the area equals the limit as the norm of the partition approaches 0 of this. And we know this is called the Riemann sum. And then eventually that leads, of course, to the integration. Boom. Okay. So what we did as a general rule in Calc 1 was, once I could identify the ith area, once I could find an arbitrary rectangle, rather than go through the entire process, we just sort of leapfrogged all the way to the end because we knew what the answer was supposed to look like. And that became very seamless. And then we used this for volumes on rotation and all sorts of other things. Now, suppose that my region cannot be integrated xy, that I'm going to have to do some sort of polar transformation. And that's exactly what it's called. It's called a transformation. You'll learn more about those in higher level classes, but I can't integrate in exactly the same way because I'm not going to be integrating x and y stuff. I'm going to be integrating r theta stuff. So first thing we're going to do is remind ourselves of a very, very huge important identity. Okay. This is the center of the circle, so this is called a central angle. If I picked a random spot within the circle to create this wedge, then it would not be true. This is the radius. This thing right here has area A and it has arc length S. Does anybody remember what the pie-shaped wedge is actually called? It's a mathematical term. That shape has a name. Anybody?
Would just the pie area?
No, the shape. That pie-shaped wedge.
Is it a section?
Close. Sector. It's called a sector of a circle. So when you say a sector, you're not taking just an arbitrary slice. You're taking from the center of the circle. So when you have that, mom makes that apple pie and you cut it perfectly into slices, going right down the middle, then every one of your slices would be a sector of the circle. This sector, I have 3 equal ratios. And this is the critical part of the geometry we need to review. Theta is in radians. Theta is to the angle all the way around, which would be 2 pi, as area is to the area all the way around, which is pi r squared, and that is to the arc length all the way around, which of course would be the circumference. So simply, let's imagine that my picture here was, 1/4 of the circle. Let's just say it was 1/4 of the circle. Then I should have 1/4 of the angle, 1/4 of the area, and 1/4 of the arc length. I mean, that should make sense to you. If I put any 2 of these together, I get a proportion. That's the definition of a proportion. It's just 2 equal ratios. The last 2 put together is how we found surface area at the end of Calc 1. If I put these 2 together, then I can see that area equals theta over 2 pi times pi r squared, which simply is 1/2 r squared theta. So the area of the sector of a circle is 1/2 r squared times theta. Now, what if I went all the way around? What if theta was actually 2 pi? Then I'd have 1/2 r squared times 2 pi, which is, of course, pi r squared. And that's exactly what we'd expect it to be. So this formula right here is what I'm going to use for my polar conversions in a moment. Okay, so let's suppose now, totally different type of picture. And let's say here's what we have to deal with. I want to find the area bound by, and let's say I'm going to go from here to here. And that angle, let's call theta 1, and let's call that angle, how about theta 2? And I have, just some, there. I want to find that area. Oh my goodness. Well, if I tried to break this up into rectangles, that wouldn't work very well. For one thing is top and bottom would change, wouldn't it? Plus, this doesn't even look like a function. Okay, so I'm kind of in trouble here. I really can't do this using rectangles. But what if instead I randomly went this way and made sectors? So if I took my shape and split it up into different sectors, in Calc 1, we did it with using different rectangles. If I do different sectors, then I can do the same Riemann sum, but from a different point of view. So let's say this particular sector, let's call this the, I don't know, the ith sector. And if this is a sector, then this radius and this radius must be exactly the same. So let's call that radius I. But then what about that angle? Oh, that angle would be delta theta I, because I have that and then that and then that, and all of my thetas will add up. Theta 1 and theta 2 would just be my beginning and ending, kind of like the AV in the last one. So therefore, what is my ith area? Well, we just said a moment ago that the area of the sector of a circle was 1/2 r squared times the angle. So this should be 1/2 ri squared times delta theta I, that is the exact angle that I'm dealing with here. So then my overall area can be estimated by the sum from I equal 1 to n of 1/2 ri squared delta theta I, where the thetas run from theta 1 to theta 2 in my picture. Those would be constants. Maybe it's from 0 to pi over 3 or something, something like that. And now the area I can say is equal to the limit as the norm of the partition approaches 0. Well, hold on a minute. Before, the norm of the partition was the largest such delta x. If the biggest delta x is approaching 0, then all the delta x is approaching 0. What would the norm of the partition be in this case? Anybody want to try that one?
Delta theta.
Delta theta, as the biggest delta theta is approaching 0. That's like saying I'm just going to keep subdividing this further and further and have bazillions of little angles. So this would refer to the angle approaching 0. Then that should translate directly into a definite integral from theta 1 to theta 2. Those are constants. Now the problem is it appears here that I have two different variables. I don't. I only have one variable. What's my independent variable in this problem? We did it yesterday. Is it r or
Theta.
Theta. So remember what we did yesterday. We said r is always a function of theta. So in my Riemann sum before, I used f of x. I didn't write y. I wrote f of x. Oh, so that's r of theta. So think of this as r of theta. So I'm going to have r of theta squared d theta, and you can put the 1/2 inside or outside. Now, our hope is that this is something that is not terribly taxing to integrate. Okay, and for the types of problems that we deal with, you're going to have sines and cosines and not a whole lot of other nasty stuff. So this is how we find the area using polar coordinates. So let's do a few examples of this. Okay, and that is the formula, and we use that in Calc 3 as well. All right, let's start with a really simple one. Okay, and I'm going to give you a reminder. One of the most common things that's going to come up, because my R's are often going to involve just simply sines and cosines, I'm going to have to integrate R squared, which means it's common that I'm going to have to integrate a sine squared or a cosine squared. So I wanted to remind you something that you already know, but you know that the cosine squared of theta is 1/2 1 plus the cosine of 2 theta. And the sine squared of theta is 1/2 of 1 minus the cosine of 2 theta. Because if I end up with an integration that looks like this, I have to change it to this in order to perform it. And it is, again, often the case that that's exactly what you're going to have. So here's the first problem. Let's find the area bounded by R equals 4 cos theta. Now I'm taking a problem that we did yesterday. Okay, we actually did 4 cos theta yesterday. I just wanted to remind you of something. So when I'm setting this up, okay, it's not a bad idea to try to sketch the picture. Does anybody remember what this one was? What it ended up looking like? Just curious. Remember?
A circle,
It was a
offset to the right.
Yeah, so it was, you know what? Sorry, I should draw my circle, then draw my axis. I can do that much better. All right, so there's my circle. Now I'll do my axis. In fact, we know we showed yesterday, this is a circle of radius 2 centered at 2, 0. So do we already know the answer to this question? Do we already know what the area is?
Sure. It's half the total area, right?
The area of the circle. Do we know the area of the circle?
Pi r squared.
So therefore, what's the area of the circle? What do we already know?
4 pi.
Yeah, so this is 2 squared. So the area is 4 pi. Now, the reason I'm doing that, you're never going to know before you start. We want to do the calculus. We want to set it up. I'm cheating kind of because I'm figuring out the answer before I start the problem. This will be the only time probably the rest of your life you'll actually be able to do this, because I want to make sure when I do the calculus that my setup is correct. So at the end of the problem, if I get that answer, then I can be pretty assured that I did it right. But this is a really easy thing to make mistakes on. So my integration is going to be the integral from something to something of 1/2 4 cosine theta quantity squared d theta. Okay, I said something to something. What is the something to something? What are my limits of integration? That's the part that's not entirely obvious. Is it 0 to 2 pi? Is it something else? Is it a pi over 2 to 3 pi over 2? The question is, I don't know yet. So let's hold that thought for a moment. I need to integrate this. I'm going to have a cosine squared. So what I want to do first is I want to simplify this quantity right here. I want to do that outside the integration. So that would be 1/2 times 16. So that's 8 times the cosine squared of theta. Because I have a cos squared, I've got to use the double angle formula. So this is 8 times 1/2, 1 plus the cosine of 2 theta. Sorry, it's ugly. So that's going to be 4 plus 4 cosine 2 theta. Is that right? I think that's what we have. So this is whatever to whatever of that. And that integration is simple. So what is this integration? Anybody? The antiderivative of 4 d theta would be if you're thinking, you're doing it wrong. You're integrating a constant. Why are you thinking?
4 theta.
4 theta. Oh, see, it probably is involving an inverse 10 or something. I don't know, maybe an exponential. And now I'm integrating a cosine, so it probably involves a sine plus or minus, and what's the coefficient? Remember, always think what's the derivative going that way. So what would this be? Plus minus.
Chain rule 2 sine theta.
Yeah, and then evaluate it from whatever to whatever. Now, we still haven't figured out what whatever to whatever is. So I'm going to go back to our picture, and I'm going to give you a simple statement. When the shape is centered at the origin, then it's generally a good rule of thumb that it's going to be 0 to 2 pi to complete the shape. That's going to be true the vast majority of the time. This shape is not centered at the origin. It still might be 0 to 2 pi, but it's probably not. I got something in my eye there. Okay. So if I was going to make a little table of values here, okay, well, let's start with 0. When theta is 0, r is clearly 4. When theta is pi over 2, r is clearly 0. When theta is pi, r is going to be negative 4. So that means when theta was 0, I was here. As my angles increase to pi, that's exactly what just happened. Or excuse me, pi over 2. Now, remember what this means? This means in the opposite direction. Oh, so as my angles, so now as my angles are going towards pi, all of my r's are going to go this way. So, I'm doing this. When my angle is pi over 2, I'm here. Now, when I start going this way, all the r's are going to be negative, which means that as I get to pi, I'm here. So in simple English, this circle just completed itself from 0 to pi. If I go 0 to 2 pi, that will involve 2 revolutions, and that would be incorrect. In fact, what would be wrong with integrating to 2 pi in my final answer? What do you think? Anybody? If I integrate 0 to 2 pi.
You have the second, or you have your primary value multiplied by 2.
It's going to be multiplied by 2. Yeah, it's pretty easy to see if I just put it in. So if I go 0 to pi, the sine of 2 pi minus the sine of 0, 0. Zero to pi. If I had gone 0 to 2 pi, my answer would have been 8 pi, which would have been 2 circles. So I'm working backwards. I can see it can't be 0 to 2 pi. That would have been twice as big. This is never a bad idea, but you always have to figure out how much is it going to take for me to complete my thing. Now, again, if the thing is centered at the origin, it's probably 0 to 2 pi. So this wasn't terrible, but it also wasn't obvious until I figured out the 0 to pi. The algebra, nothing about it. There's nothing about the algebra that's difficult. Now, we did a problem yesterday. I believe we did, see if I can remember. I make up problems off the top of my head, but I think we did 8 plus 8 cos. Does that sound right? I believe is that the cardioid we did yesterday? So we know what that looks like. Looks like this-ish. Okay, so this one here, when theta was 0, I was here, and as I moved around pi, I was here, and then 2 pi. This definitely took 0 to 2 pi to complete. Okay, there's no question. So here's what I want to find. I want to find the area bounded by this shape. Now, is this kind of circular-ish? What do you think? Ish. Is it kind of circular-ish?
Sure.
Yeah, ish. So if it's 16 from here to here and I think it's 8, you kind of say, this isn't that far off. This isn't that far off from a circle of radius 8. Does that make sense? It's not that far off. It's not a circle of radius 8, but it's, it's in that ballpark. Well, a circle of radius 8 has area 64 pi. And the reason I'm doing that is if you believe this is kind of circular-ish in nature, then you would expect a final answer that wasn't way different. You see, a circle of radius 8 is 64 pi. If I end up, with 1,000 pi or 1/2 pi, so that seems really far away from the circle. I would expect an answer that's not terribly different. I don't know how close is, but definitely won't be too far off. So since my integration is going to involve 1/2 r squared, this time let's go ahead and calculate 1/2 r squared before we start the problem. Okay, so 1/2 r squared is 1/2 8 plus 8 cos theta. There we go. That's terrible. Let me try that. Sorry, I can't even read my own writing here. Start that again. 1/2 8 plus 8 cos theta quantity squared. Now notice our r is actually a function of theta. That's pretty simple to see. So 64 times 1/2, 2 times first times last times the half, 64 times the half. All right, well, that's easy enough to start. So then let's change this. I need this 1/2 1 plus cosine of 2 theta. So I'm going to distribute the 32 times the 1/2 and then into the quantity. So this is 32 plus 64 cos theta. Okay, 32 times this, so plus 16 cosine of 2 theta. Because I have two constants, let's go ahead and add them. So I have 48 plus 64 cos theta plus 16 times the cosine of 2 theta. That is going to be my integrand. Okay, when all is said and done, I'm integrating that. So now I can say area equals the integral 48 plus 64 cos theta plus 16 times the cosine of 2 theta d theta. There we go.
And Professor, is that 1/2 r squared? Or just r squared?
I got a 1/2 right there.
I mean, because you kept on each line, you kept writing equal, 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 equal. And to me, it sounds like, well, the 1/2 r squared will equal this, keep equaling
This
this.
is 1/2 r squared. Yes.
And the line underneath it, is that 1/2 r squared or r squared?
You just asked me that. What's 1/2 of 8 squared? What's 1/2 of 2 times 8 times 8? What's 1/2 of 8 squared? Yeah, I walked through that. That should be really clear. That's, yeah,
Okay.
that's 1/2 r squared. Yeah. All right. What are my limits of integration? They're up there somewhere. Anybody for the limits of integration?
0 to pi.
0 to 2 pi. Is that important? Yeah. If I have different limits, I absolutely will get a different answer. It actually would be quite different. So when I integrate this, integration 48 d theta, 64 cos theta. What's the antiderivative of that?
$32.
64 cos theta. You're thinking of that one. I don't think you guys have had enough caffeine today.
Oh, it's negative.
64 sine theta.
Just 64 sine theta, yeah. And then the last one's going to be sine 2 theta. So what's my coefficient? And what do you have to differentiate to get back to here?
32.
No. Multiplying by 2, so
8.
about 8. And then I'm going from 0 to 2 pi. We got a little rust here, folks. All right, now here's what's really beautiful about this. Sine theta from 0 to 2 pi, both 0. Sine 2 theta from 0 to 2 pi, both 0. Oh, so what's my final answer? So the final answer is
48 theta.
96 pi.
how about 96 pi? 48 theta is the antiderivative, 96 pi. Now let's go back to our Purdy picture. We said it was circular-ish, right? I could definitely draw a circle of radius 8 inside of there. But there's a whole lot of stuff left over, isn't there? That's why the answer is not 64. We said this is, not that dissimilar to a circle of radius 8, because we could see a circle of radius 8 somewhere in there. Our answer is basically 50% bigger. That seems reasonable, or at least it ought to seem reasonable. If this was in the hundreds or thousands, I'd be a little bit suspicious. If this was small, I'd be suspicious. But the size of the answer, yeah, I'm okay with that. That we have no errors. Turns out there was nothing difficult about the integration. We had to be careful with our coefficients. Fairly routine problem. Now let's do the next level of the same problem. All right. Find the area. How about, I'll take the same function. Find the area. How about outside R equals 8 plus 8 cos theta, and inside R equal 8. Ooh, this kind of looks evil. Now here's where a picture will be really, really helpful.
Don't you have those backwards if R equals 8 plus 8 cosine has greater area than R equals 8?
Yeah, but R equals 8 is not inside that one. So let's draw a picture. There we go. Does that make sense?
Yep.
That's why, by the way, and I don't say this joking, that's why you always sketch a graph. In Calc 1, you always sketch a graph, because if you don't sketch a graph, sometimes it's very difficult to determine your boundaries. Now, there's several ways I could have asked this. I could have said between the two, which would be here. I could have said outside the circle, inside the cardioid, that'd be here. I said outside the cardioid, inside the circle, so that's here. Does everybody see that? So that's what I'm asking for. But I could have asked for this region. I could have asked for this region. I just a couple word changes. But the important thing is that I know what the picture looks like essentially. Now, here's something do not take for granted. I need to know where these intersect, because if they intersect somewhere out here in the first quadrant or somewhere over here in the second, that would make it really, really difficult for me to figure out my limits of integration. So all we need to do is set these two equal. So let's set 8 plus 8 cos theta equal to 8. Well, then that would mean that 8 cos theta equals 0. So that would mean that cos theta is pi over 2 or 3 pi over 2, which means they intersect right here and right here. Would you say that's a really convenient place? Yeah. Anywhere else that would have been really inconvenient. They intersect right on the axis. So in my picture, if that's pi over 2 and that's 3 pi over 2, what are my limits of integration going to be?
Pi halves to 3 pi halves.
Good. My limits of integration clearly go that way. So it's going to be from pi over 2 to 3 pi over 2. Okay, I got that part nailed. Now the problem is, what is my integrand going to look like? So now I'm going to take you back. We're going to go on our way back machine here, Calc 1. Y equals f of x, y equals g of x from A to B. Oh, how did you do this one? Do you remember?
Take the area of yf minus the area of gx.
I can do two separate integrals, but you never do two separate integrals. You did the integral of, do you remember that? You did the integral of the difference. Oh, okay. That height is f minus g. So you're correct. You could say, I can take the big area, calculate it, subtract the little area. I can take the area and subtract out. Well, yeah, but that seems like a lot of extra work. Instead, what if I said from the center, let me just draw an arbitrary piece here. Oh, this is what I want, isn't it? So here you said F minus G. Here I'm going to say 1/2 R squared, this R squared minus 1/2 this R squared. Does that make sense? So if I want the area of this portion of the sector, what I'm going to do is take the big sector and subtract out the little sector. If I wanted this, I took the big rectangle and I subtracted out the little rectangle. We did the same thing. In fact, keep it really simple. Just in general, let's suppose I have two circles and I want the area between the circles. Wouldn't all of you say find the area of the big circle and subtract out the area of the little circle? Isn't that automatic at that point? So I want, if I take the entire sector, that's from here to the circle, and subtract out the sector that's from here to the cardioid, that gives me the in-between. And you notice the circle is always on the outside. Okay, they never switch places. So when I'm finding my arbitrary area, my ith area, I'm going to take the outer, which is the circle, and I'm going to subtract out the inner, which is the cardioid. This is going to be what I'm going to choose for my integrand. Again, bigger minus smaller. So if we do this calculation, this will be 32 minus 64 cosine minus 32 cos squared theta. Okay, so far so good? Well, I like that. Now, what do I got to do here? Well, that's negative 64 cos theta minus 32 times. Now I'm going to go ahead and write. I don't need this anymore. I'm just running out of room with this here. 1 plus cosine 2 theta. Okay, so now I've got negative 64 cos theta, negative 32 cos 2 theta.
Is it 32 or
Oh, did I?
16?
Thank you. I'm sorry. I'm writing too fast here. That should be a half. Thank you for catching that. That should be a 16. And I don't think there's anything else we can combine. Now, what seems odd to you is that all of my terms are negative. How's that gonna work? Is that gonna completely mess me up? Well, not necessarily. Let me.
Did you also not take the half of 32?
Did I not take the half?
Isn't it 1/2 times 1 plus cosine 2 theta?
Thank you. You know what? Let me do this again. I was trying to write too squished. You're absolutely correct. This should be negative 32 times 1/2 1 plus cos 2 theta. In my effort to write really small, hold on, let me get rid of that. Can't stand it when phones ring around here. So this would be what? Negative 16 cos 2 theta. That's what we should have. Along with this, I think that's all we have. Is that right? Is everybody okay with that? Now, what's odd is that everything is negative. You go, oh my goodness, but my limits of integration may take care of that part. So that may end up not being an issue at all, by the way. So let's go ahead. I think I can squeeze it up here. So then our area, I'll use black so we can follow along a little better. Our area is the antiderivative of this part here. D theta, and we said before from pi over 2 to 3 pi over 2. Does that sound right? Everybody good with that? And that's why we needed the picture to make sure our limits were good. So let's go ahead and do this. So the first antiderivative would be, what's the first antiderivative?
Negative 64 sine theta. Negative
Then
16 theta.
minus 16 theta, then it's gonna be a sine of
Negative
2 theta,
negative 8.
negative 8 sine 2 theta, and I'm going from pi over 2 to 3 pi over 2. All right. So what is the sine of 3 pi over 2? What is the sine of 3 pi over 2? Anybody?
-1.
-1. Oh, so this will be positive 64. Negative 16 times 3 pi over 2 would be minus 24 pi. Now I have sine of 3 pi. That's 0. Okay. Sine of pi over 2, we know that's 1. So this will just be minus 64. Minus 16 times pi over 2, so that'll be minus 8 pi. Sine of pi, again, that's 0. Okay, so what does this give us? 128 minus 16 pi. So our answer is, oh, by the way, is our answer positive? Yes.
Yes.
What would be a good idea at this point in any problem to do? And this is not a joke, especially if you don't recognize the numbers. You got pluses and minuses and pi's, and maybe you got roots. What's always a really good idea at this point?
Multiply by 3.14.
Plug them in the
How
calculator.
do you do that? God, no, no, yeah, no, that was a yuck. Just calculate it. You don't approximate. You don't ever approximate an irrational number. You just enter the irrational number. Why would you stick it on a calculator? To determine if it is
Positive.
positive. If you're finding area or volume or surface area or arc length, it's impossible to get negative. It's impossible to get 0. Ooh. So what would it mean if I got a negative answer here? Let's assume that your algebra, you didn't mess up the algebra entirely. I mean,
The limits. The
probably the limits of integration. It's probably the wrong limits, because I'm assuming that you checked your algebra, that you go, okay, I feel pretty good. I'm pretty good about my integrand. You did everything right. You did your evaluation. Now, by the way, could it also be your antiderivatives? Because of the plus or minus signs, could it also, is that where the error could also come from? Yeah, so it could mean, and you know, when you're working with sines and cosines, it's always the positives and the negatives that give you issues. You know, derivative versus antiderivative. Oh my God, was it plus? Was it minus? Because sines and cosines, plus and minus signs change, that is one area where you'd have potentially issues. And the other is, of course, just switching the limits of integration, getting them backwards. Always just real quick check. Did I get a positive answer? Or did I get a negative answer? And if you got a negative answer for something where you're doing a measurement. Now, can an integral be negative in general? Is that legal for an integral to be negative?
Sure.
Can an integral be 0?
Sure.
Yeah, but not when you're finding a measurement. You're finding an area. You saw physically there is an area there. That can't be 0, because that would mean it was an incorrect setup or an incorrect procedure that we did it. So that's always a good idea to do it, just a really quick check. Next semester, for example, we're going to be doing things with motion. You know, we launch an object up in the air, it's going to eventually turn around, it's going to come down and hit the ground. And I'll say, you know, what is the impact velocity? Things like that. Well, you know, the impact velocity really ought to be, especially if you fired the thing, you know, 100 feet off the ground, the impact velocity really ought to be a little bit more than the initial velocity, because it sped up, you know, and certainly the impact velocity can't actually be less, because then gravity's not working. So I tell students, you know, check your answer, because it's usually going to be some irrational roots, all this. So check the answer, make sure that it makes sense, you know. So if I start 500 feet in the air and I shoot an object up in the air, when it comes back to 500 feet, it's going the same speed in the opposite direction. It has 500 more feet to fall. Of course, it's going to speed up. So if their final answer is slower than it took off, then the final answer is impossible. And I ask people, you know, check your answer in that way. And a lot of times people don't, and they'll get an answer that's not possible, and they didn't check it. So always check your answers, because that's the easiest part of the problem. So here's what we have. We have the area of a region that has to be determined using polar coordinates because we can't do it using rectangular. So then we use the fact that the area is the integral of 1/2 r squared d theta, and then we go from there. Hopefully we get an integrand that's fairly simple. But like I said, since most of these are going to involve just simply sines and cosines, nothing complicated, double angle formula is the worst that you're going to have in the problem. And the rest of the problem is pretty straightforward. All right. So we are now done with content for Calc 2. All right. Next semester, day 1 starts with vectors. And I mean vectors like 7th grade math vectors. I mean, so remedial that nobody has trouble. And then we, hit the ground running and we go really fast. But we start with not calculus for the first month. Literally no calculus the first month of Calc 3. It's all about vectors and understanding motion and things. Then we get to the calculus. So the stuff we're doing now, you won't see till much later in Calc 3, but you will see it probably by, October-ish. Now, we have an exam tomorrow. We have a party, a math party, that you're encouraged, of course, to show up and show off and strut your stuff and all that kind of stuff. Like the previous exams, I had to really work this one because it wasn't the same type of exam, but I like giving you choices. So again, I've given you more problems than you have to do. I don't usually do that on the 3rd exam just because there's so many different types of problems, but I was able to rewrite it and manipulate it so that you have choices. You don't have to do every problem. And if you get stuck on a problem, you can, of course, move on to the next problem. Same rules as always. You can write down any theorem, formula, or definition that we've learned in this class. Now, what you're going to write down for this test is probably going to be very different from the previous tests. So we have things like, for example, the binomial formula. Okay, there's a few things that we know. Now, we know the power series for e to the x, sine x, cos x by now. You can write those down if you need to. I'm going to tell you the power series for e to the x and ask you to tweak it. I'm going to tell you the power series for the cosine and ask you to tweak it. So you really don't need to write them down. But what about things like the geometric series, the formula? Yeah, we've done that one before, but you guys know how to translate back and forth. How about the general equation of a parabola, right? The 1/4p x minus h quantity squared plus k. How about the general formula for an ellipse or the general formula for a hyperbola, right? In the a squared plus b squared in the denominator form. These are things that might be a good idea to write down just to make sure. We just had a quiz where you had to find first and second derivative of a parametrically defined curve, and you also had to find arc length. That is not standard fare in XY world, right? That's different formulas altogether. Those might be things you want to write down. So again, both sides of a 3x5 card, theorems, formulas, definitions, not Calc 1 formulas, right? There shouldn't be any derivative or integral formulas at all on there, but then again, I don't think you're doing any integration on this test anyway, so that's not really an issue, except arc length, I guess. That would be it. And that's probably pretty low level integration. Let's see. I think that's about it. Does anybody have anything that they can think of that I haven't mentioned in terms of prep?
So on the practice exam,
I'll do that during the review. I just wanted the logistics part. We'll do all the practice tests.
How many extra questions? Like how many questions out of what questions do we need to answer? Is it like out of 20 or something?
Something like 15 out of 20-ish, something in that range. I don't know exactly, but yeah, I mean, there's more problems than you have to do. So again, the ones that you know well and you can do fast, you want to do those and get them out of the way, obviously.
And there is mandatory questions from each section. So
no, not in this case. They're just questions because they're all mixed together in this case.
Oh, okay.
So
like for example, if I'm not feeling too comfortable with something and I don't have time to get it down,
skip it.
I can. Okay.
You can skip it. Yeah.
You can just do evil trig.
Yeah. I have an extra page for Yaman that just has like 10 evil trig problems.
That's why I didn't do so well in exam 2. You didn't give me an evil trig.
That's my bad. I need a reminder, like, okay, throw some evil trig on there for you. Okay, so let's take a short break if you don't have any other questions. And as always, I'm going to email you the exams about 10 minutes beforehand, just because I want everybody to have time to print them out or write it down, do whatever. Again, I prefer that you print them out so that you are not nose to a computer screen for 2 hours. That's the only reason. That, and the fact is that it's still an issue today alone. I had 3 different quizzes turn in between the 2 classes where the person did flawless work. They just wrote the problem down incorrectly. They did a completely different problem than the one I asked, because this is on a quiz. Almost everybody prints the quizzes, but some people don't print the quizzes. They write them down and they sometimes miscopy the problem. That's the other reason why, if you can print it, it's better. But if you can't, that's all right. Let's again take a short break. By the way,